Good afternoon. Okay, right. It's indeed a pleasure to be here. And I'm in this room after a long time, I think it's probably. And every time when I gave a talk here, it was always based on some astrophysical issues we address using spectroscopy. It could be low resolution, high resolution, moderate resolution, and things like that. As one gets old, it is the ability to do analysis and all are very difficult. So I moved on to not asking question in nature, just to produce whatever we can and then be happy with it. So that is an attempt to make galaxy formation simulations at IUCAA. I will just summarize what we are doing and what is the motivation in doing this. There are two reasons why we started doing this. One is that my general curiosity is that whenever we do interpretation of any observation, there is nobody to check whether your interpretation is correct or not. Whereas if you have a simulation and if you analyze the simulation like an astronomer, who I am, so I am trying to analyze in a particular way, the approach we are taking is that if I go and simulate something and take data out of the simulation, like the way we do in real universe, and you make interpretation and check whether the reason behind what you are seeing is exactly what you are interpreting. So this is much more interesting. It is like a toy model, not necessarily the reality, but it gives you insight into what you should be doing. It's just an evolution of me as a human being, starting with pure data analysis. Now I am going to pure simulation. So this is also is the journey which I will go through. So the way this talk is structured is that first I will just introduce very basic level what we want. If you say that I want to form galaxy, what exactly we are talking about. Second thing is that I just stop there and just move on to JWST and just tell you what JWST is seeing and what kind of thing which will be interesting. And then I will try to connect these two things, saying that where is the niche area we have and why we think that today we can do simulations like the way it is being presented today here. Why can't we do it sometime back? I will just explain it in a simple way. And since I don't know timing, how far it will go, you just tell me wherever you want to stop and we can comfortably stop. And I'm sure like I would have conveyed whatever I want to convey in this talk. So first I'll start with some standard 5-6 standard slides which we will use for a public talk. The idea is to just introduce you the challenges one is going to face. First of all, this is the picture we know very well, picture taken in different wavelengths. Definitely if I am going to talk about galaxies, I have to worry about how it is going to appear in different wavelengths. And that doesn't mean that we have to worry about the spectrum of a star itself, but that's what we have been told. If you take spectrum of a star, it peaks around somewhere, a collection of stars will peak around somewhere. In UV, it will look different. Infrared, it will look different and all. But what this plot tells us is that you have to worry about stars, you have to worry about gas, we have to worry about dust, you have to worry about plasma. So I'm not going, because since you are all astronomers, I'm not going to spend time on this slide. Basic idea is that whenever you are going to, if you are thinking of simulating galaxies, make sure that you will be visible to all wavebands. That means make sure that your galaxy contains plasma, galaxy contains cold gas, galaxy will contain some amount of dust, and that physics, whatever you are going to see, will be seen in reality also. I'm not saying that you are going to mimic everything thoroughly. Second thing we have to worry about is that in analytical models, whenever we do models, if somebody gives you star formation rate or some rate, immediately we'll associate some flux to it. We'll say if this much stars are formed, this much light will come in UV radiation because the scaling relations are given to you. All of you might be using, if you find a magnitude, immediately you will say, I'm finding star formation rate. I'm going to find stellar mass and things like that. These are the ingredients of galaxy. Are we sure we can do it? So take an example of a simple galaxy, depending upon what its age, it looks very different in spectrum, right? You will see a lot of UV light. So we also want to make sure if you are generating some galaxy which contains old stars, new stars, recently formed stars, we have to capture their thing through spectroscopy or narrowband imaging. So that means that this aspect should be ingrained into the simulation which you are going to build. Lastly, when you look at dust, you are not only looking at dust in terms of extinction, you should also worry about dust in terms of emission, which become interesting because some of the galaxies which if you look at nu, I nu or lambda, I lambda, where you see power at whatever logarithmic intervals, you see that some of them will peak around optical, some of them will be peaking around near infrared, some of them will peak around far infrared. Why this is important? If you are working at low redshift 0, there is no problem. But if you are looking at high redshift galaxies, for a fixed wavelength, you are looking at the galaxy at different intrinsic wavelengths because of the cosmological redshift. Which means that the way you will look at a galaxy, where it is, will depend upon where I am going to place at different distances. So the full knowledge of what you call spectral energy distribution is essential. So our idea is, when we build these models of galaxy formation, we'll also try to capture this idea of what kind of, so that means this kind of physics we have to put by hand. It is not that you are going to get it hydrodynamically. Hydrodynamically is a numerical number. Everywhere you have to put some physics so that you can get. Of course, what is more striking is that this kind of simulation one can do. We will say, like, because I myself have done some couple of our collaboration with Kandasamy Subramaniam, we have 2 PhD students worked on generating galaxies starting from analytical models. Problem there is that each galaxy is an isolated region, which is self-gravitating region. We don't worry about what it does to the surrounding medium. Here is a beautiful example, and you know this combination of 3 galaxies. This optical image, if you look at, you see 3 isolated galaxies evolving on their own. But if you look at the same region in 21 centimeter, you realize that these 3 galaxies are completely connected. Other way of saying is, gas in an individual galaxy is distributed over a much larger area compared to dark matter or star. So if there are 2 of them coming close to each other, any interaction will be imprinted, its signatures, in the form of what happens to the gas distribution. Which means that it is absolutely essential for us to track gas particle and what happened to gas particle at a smaller distances and interacting timescales. Lastly, the same picture now taken with a much deeper image, and you're beginning to see a lot of interesting stuff. Start seeing these kind of blobs which are appearing. These are known as high velocity clouds. These are hydrogen clouds hanging around in galaxy, even in our galaxy, hanging around over large distances with high speed, and we really don't know what they are. Okay, so if you are building a model, we should capture such physics like what you call high velocity clouds. And also, if you look at one of the galaxy, this galaxy, it looks like completely simple. It's called M82. If I tell the name, then you know that it is very famous galaxy for galactic winds. Whenever we talk of galactic winds, this is what is being shown. Clearly, this is the galaxy which is interacting with 2 other galaxies. If I look at the optical image with H alpha image, and you see these biconical outflows, and it is well-known prototypical example of outflows. So the question is, we worry about interaction. When you go into the inside of the galaxy, you should worry about hanging clouds. This also goes by the name circumgalactic medium. Gas clouds which are hanging beyond the galactic disk, we need to model them. And also we need to see whether the galactic disk can sustain outflows triggered by either star formation happening in the disk or by the way you are growing the black hole. Okay. That brings me to another component which you have to worry about. The component which, again, based on the rotation curve, we know the dominant mass component of a galaxy is the dark matter component. Okay, we believe that dark matter decides everything. And if you take cosmology, the ratio of dark matter mass to baryonic mass will be 6:1 roughly. The 6 times more massive. But if you do the same thing in our galaxy, it's much, much higher. It's factor 100, right? Even though rotation curve you do, you go and measure the mass of our galaxy, look at mass of the galaxy which you can get from star as well as gas. This is not factor 6. It's much, much higher. That means there is some physics which is going on, which is going to remove the baryons from whatever is the visible universe. So we have to worry about how to keep either baryons are removed from galaxies efficiently, or baryons are there. They are in a state which is invisible to us. Okay. So this is either you hide them or you throw them. This is an open problem. This is called missing baryon problem. So if you want to understand this, we have to also worry about whether that happens in simulation, because we are putting by hand everything. We can ask this. So presence of dark matter, how dark matter is going to interact with stars, how it is going to interact with gas is becoming important. So just I built So we talk about star, gas, plasma, dark matter. The last but not the least amount is the central black hole. We know almost every galaxy has a central black hole. And is this central black hole just independent of the galaxy itself? Can I put some randomly some mass in this? No, because we know that there is a standard relationship between mass of the galaxy and mass of the black hole. More massive is the galaxy, the central black hole is much more massive. So this is also interesting. That means the process which creates black hole or which grows black hole has some link to the way a galaxy is growing. This is a very intriguing problem for me. If you want to see what is the sphere of influence of a typical black hole, means that if I go closer, it will attract me by gravitational thing. If you take a 10 to the 8 solar mass black hole, the size what we are talking about is like our planetary system, few AUs. Okay, so if you are beyond few AU, it cannot gravitationally interact with you. Okay, and black hole grows by gravitational attraction of matter into its center. So now if you take the event which is happening in few AU scales has somehow linked to the event which are happening around tens of kiloparsec. The size of a typical galaxy is much bigger than whatever you have in a region of influence of black hole. So this connection has to be established as well. So this is what led us people to believe that when we are growing black hole, you have to have some kind of feedback, means like black hole formation or black hole growth, give something back to the galaxy so that the galaxy somehow react to how the black hole is grown. This feedback process is what is being talked about. So this is nothing new I have mentioned. These are all well-known stories. That's why it is in popular level lectures. These problems are well known. So this has been addressed in different ways. One of the basic ingredients we understand in forming galaxies is the following. We believe that there is an initial perturbation which happened in the early universe. And these perturbations are mainly in the density and velocity field of the dark matter particle. And any region which has slightly higher density, elevated density, will grow because of gravitational attraction. Gravity is simply an attracting force. So if you collect material into a smaller volume, it will keep collecting material in the surrounding region. So there is a gravitational instability which grows. So when you have dark matter and baryons together, if I scoop little bit of region, of course, I'm going to ignore for this thing, there is an expanding universe, you have to worry about that. Two particles try to expand, but you have to bring them together. That part, let's leave aside. Suppose we have achieved that, a small region where dark matter is now collapsing because of its own gravity, then what happened to the gas particle? Gas particle will follow the dark matter because it will respond to the growing gravitational potential. If this gas particle can cool, fragment, and become stars, you have galaxy. Otherwise, you have some dark matter halo, which is hanging around in this. So basic ingredient is that you will have some regions in space where perturbations in the density and velocity field in the dark matter thing clumps material, and each region can be a potential galaxy. But gravity being attractive force, these two regions will start attracting each other and they will bring them together and start growing a bigger region. So the idea is like this is called gravitational clustering and growth of gravitational structure through gravity. This is very simple models. All this has been worked out. So what is needed is you need to have a basic perturbation which is happening in the universe, some initial conditions. Then you put some particles. Basically, you have dark matter particle together with gas particle. And this gas particle and dark matter particle in some region will satisfy the condition that they are self-gravitating, they are ready to become a galaxy. So once you identify these galaxies, now you can go and do physics with it. So you say that what is the condition I put so that I am given this much amount of gas, how I can convert that gas into stars? What is the efficiency at which I can convert gas into stars? So for that, you will have conditions like gas should cool, it should become dense, and it should become so dense that in the central region you can trigger nuclear activities. So you can put some conditions saying that what is the requirement for, given a gas particle, what is the requirement that you will have stars being formed in that region. Having formed stars, you have a problem. Then you have to figure out that what happens to the stars. So you go back to the stellar evolution. I think you people will know much more than this. This is one of the center where a lot of focus is on stars. So you now know what happened to the stars, and they die. When they die as a supernova ejections, what happens to them. When they live, stellar wind can influence the surrounding. When they die, supernova can influence the surrounding. So the basic ingredient is that you have to worry about dark matter. You have to worry about what to do with baryons. When you take baryons, you have to find some reason whether the baryonic particle or in your simulation or in your model, whether it is good enough to be a star. That means the way you will do simulation is that you will do association of various probabilities to a region. Because real life things are really happening. Stars are forming means actually stars are forming. In simulation, stars are forming, meaning some region you declare it as a star. It is not that you are on its own, it is going to shine or it is going to, nothing. We are going to mimic everything. So every region in your simulation, you will associate a probability. What is the probability that this region will become a star? Having associated probability, that means then you can do one more exercise. I collect all the region where the probability of forming star is above some threshold. Now I look at the stars and assign one more probability. Which one is ready to blow as a supernova? So you have to write down set of probabilities and conditions, and interactively you have to solve them. So this is the basic ingredient we need in a simulation. So you need to deal with gravity over a larger volume, and you have to also deal with physics at a smaller volume. So this is what is known as challenges in the dynamic range of the simulation. Okay. So I'm just dragging you into this. So basic idea is that we will set up some initial condition over a box or something. So what should be the size of the box? Again, if you are interested in solving cosmological problem, one of the things we have been told is that universe is homogeneous and isotropic. That means you should, to apply to these models and to get a realistic understanding of our universe, the box should be sufficiently big. Whatever you call as universe should be sufficiently big. Typically, people say that a sizes of the order of hundreds of megaparsec. If you simulate 100 or more, you are typically into that regime where whatever you are seeing statistically can be attributed to what happened to in galaxy. This came by practice. Don't ask me why 100. Why not 150? 150 is better. 75 may be a problem. So 75 means you may miss out some of these large scale structures may not be forming because you are missing out such scales in your box. Okay. So what are we up to? So I will just motivate few things from the past before we go into our simulations and whatever we are going to do. One of the quantity which people are interested in whenever you are doing galaxies is what is known as galaxy luminosity function. What is luminosity function? Luminosity function is you just count number of galaxies per unit volume having luminosity between L and L plus DL. Okay, this is what is known as luminosity function. It's just a number counting. So these points what you are seeing is what is known as observed luminosity function. Of course, we are astronomers. We don't like luminosity. We write them in terms of absolute magnitudes. Okay, so this function has a form like this. There is typically a power law and an exponential cut. This goes by the name Schechter function. If you follow galaxy. So the first in early 1990s or early 2000, people asked this question. So we are thinking of universe forming from dark matter. Okay, take pure dark matter. You just introduce gravitational fluctuations in them. After some time, these dark matters are clumping into small isolated gravitating objects. So now what you do is that you go and count. Now you can count them. You can simply count how many objects of self-gravitating objects with mass between m and m plus dm. Instead of luminosity, here you are doing with mass. This goes by the name mass functions. So you can actually go and look at your simulations, or it can be done analytically also. You can look at it and ask the question, if I start with the initial perturbation of some value, how many isolated objects I'll find with mass ranging between m and m plus dm, okay, per unit volume. So you get this thing. There is you can actually see, it's also an interesting thing. There are more objects with less mass, typical of what you see in any of the scale-free distributions. You see, if you go to massive objects, they are rarer. Small mass objects are much more abundant all over the place. Then you can ask a simple question. Say that some physics, there is some connection between dark matter and stars. I say that every galaxy, there is a fixed light to mass ratio, saying that I'm not saying that dark matter is going to shine, but you can say that if there are this much dark matter, there may be proportionate amount of gas being formed. Other way of saying, if a dark matter object is big, I form more stars. If dark matter object is small, I form less number of stars. Let's assume that this ratio is fixed. This ratio is what I call it as mass, light to mass ratio. So you take distribution of matter, just assign some light to it with a proportionality. This much mass, you take this much light. When you do this, this is the curve you get. The curve you see here is the dark matter halos in a Lambda CDM model with constant mass to light ratio.
And mass to light ratio is constant for all sides.
No, but that's what I'm saying. This mass to light is not like mass to light in the case of stars. So here what we are assuming is that if I have a dark matter potential, the amount of stars I will have will go proportional to this. So I'm coming to, you can clearly see this is not the case. Because if you assume constant mass to light ratio, this is the curve you get. So even if you fix your mass to light ratio, by the one place you decide, I think this place you decide, and you vary that, and this curve pass through this. There are two regimes where you are finding it, this is exceeding. If I assume constant light to mass ratio for halos, what you find is that you expect much more galaxies which are smaller compared to what you see. Okay, this is one problem. Second thing is that if you go to at the other extreme, brighter extreme, again you predict much more galaxies than what you see. So then it is clear that you cannot have a constant mass to light ratio. Your mass to light ratio has to be smaller at smaller sizes as well as at larger sizes. So mass to light ratio being small, you can treat it as if in these objects, you have to somehow make stars form with less efficiency. If stars form with same efficiency everywhere, then your light to mass will be more or less proportional to the mass. Then this curve should have fit on top of this. It is not happening. That means this kind of dark matter potential, I have to make sure that I don't have sufficient amount of stars. Similarly, this kind of regions, smaller galaxies also, I have to make sure that I don't form stars very efficiently. So this is where people went to what is known as feedback processes. So these are characteristic galaxies of size of 10 to the 12 solar mass. If you think it is like Milky Way-like galaxy, or twice or thrice bigger than Milky Way-like galaxies. Whereas if you go to larger galaxies, typically here you are going into groups or cluster kind of regions. So this region, you suppress the amount of stars formed by demanding that there is a feedback process. This goes by the name AGN feedback. So whenever the idea is that whenever black hole grows in these galaxies, the jets and winds which are coming out of this black hole influence the surrounding region and heat them in such a way that they become useless for forming stars. So this is called AGN feedback or AGN heating. It usually happens at galaxies which are much massier than typical of our galaxy, kind of. But on the other hand, this side, we have to also suppress, this side you suppress the formation by demanding that whenever you have a smaller galaxies, when you form stars, when they die with supernova ejection, and the supernova ejection can push the gas in this galaxy to faraway distances, and if the velocity exceeds the typical escape velocity, they can just go out of the galaxy. So this side you use, because this is all theoretical ideas, I'm not saying this is what is happening. This is easy for us to understand. If you implement this is called supernova feedback. You just drive the gas out of the galaxy. And here what happened, the gas may not be driven out for large distance because this is very massive potential. The gas can be there, but you make the gas too hot so that it cannot condense and form stars. So this side you do by heating, this side you do it by evacuation. So when people implemented some simple prescription, this much star formation, this much mass outflow rate, this is the rate at which this is the gravitational potential, you can actually write down these equations, analytically solve them, and people are able to get this luminosity function. Now you can match. You don't have to do any fancy model which I was explaining to you. You can start with dark matter, but you will have three parameters. One parameter is that what you do with winds and which mass scale the wind has to start. Another parameter is that what to do with the AGNs. This is three parameter. When you are given one curve and three parameters, you will fit any curve you want. Okay? So that is the status of this. So remember now, if I want to bend the luminosity function, I will use feedback. Feedback means in those halos, I will not allow stars to be formed very efficiently. I will do something. Either I remove the gas so stars cannot form, or I heat the gas beyond some temperature so that it remains as a plasma or something and I will not form. This is the kind of understanding we have, and it is being implemented in all the simulations. So that's what it is, okay? So
feedback is not going to reduce the number of galaxies, right?
Sorry?
How you reduce feedback can only reduce the mass, but you have on the y-axis of the number.
Yeah.
How are you reducing the number? You disrupt the galaxies?
Yeah, that's all. So this side, some of these galaxies cannot
Destroy.
So they will move like this, right? So you imagine if there is a galaxy, it will move in this direction because it becomes fainter. So this is luminosity function, luminosity and mass. So if you make a galaxy fainter, the number may be same. So what you have to do is that you make 50% of the galaxy fainter. Galaxies are physically there. They will not be detected by you because they become fainter. Nobody is saying that dark matter potential is destroyed. We are just saying that they don't have galaxies, stars. It's just counting, you are counting numbers. Suppose imagine 10 galaxies are there with luminosity L. I just say that probabilistically 5 of them L become L by 2. If I go and count how many are there at L, it will be 5 instead of 10. But I would have got some L by 2, 5 of them. So if you go down in this sea, you will start seeing something going up again. That will be whatever you call low end luminosity will go up. So that one can check. Okay. Anyway, I will just skip this part because this is known to you. We basically say that the universe starts from a big bang and whatever. I think it's okay. So why are we interested in JWST? See, I will just come to it. This whatever I said is simple. It can be implemented in a full numerical simulation. But the problem is it takes huge amount of time to compute everything. Whatever I said in words is thousands and thousands of lines in code. So it will take enormous amount of time for you to simulate anything. Dark matter, simple dark matter, say I'm just saying 5 years before, if I want to take 100 megaparsec cube box and just run simple dark matter, starting from some initial condition up to redshift 0, it used to take about 1.5 to 2 months in IUCAA cluster, whatever we have. 1.5 to 2 months. But if you switch on all the processes, it used to crash. If you are unable to, it won't do. In the first step itself, it will go. That's why in India, you would have found people have never attempted to do it in this scale because of the problem that we don't have resources. Second thing is that we have to also have some approximations which will help us run this code faster. Okay. The second problem is we are also going the time scale wise. If you want to store a lot of these things, the storage thing become another headache. So if I want to, now I will explain to you, I gave you various things by hand waving arguments. Suppose you say supernova, one supernova goes off in a region. It can do a lot of things to the surrounding region, right? It can heat up the gas by dumping energy. It can give momentum by kicking the gas. Now you can decide, I take total energy available in supernova and give 10% energy to the surrounding gas, what happens? So I have done it, got the thing completed. But somebody else will come and say 10% is wrong. You should have done with 15%. 3 months work is gone. What will I do? I cannot go and change it to 15%. This is what happened in the past. And you would have seen Millennium simulation. Millennium simulation was run with a particular cosmological parameter. By the time the simulation became public, people said that those cosmological parameters are wrong. So I think the problem in running big simulations is that if you want to really compare with some observations, they are not going to be useful that way, but they give you physical insight. So you are not going to use those simulations to really model something and do something. What we realized was this simulation can be run if we improve our computing facility at IUCAA by factor 2. So that's only that much was needed. Small amount of factor 2 improvement. Second thing is that I don't worry about looking at galaxy till today. I just say that I want to look at galaxies only up to first 100 million years or 200 million years or 300 million years, which you can do it in few days. If you run your simulation, full hydrodynamical simulation with all these things can be done in 10 days. You don't need. That means this running 300 days, you can run 30 simulations where you can change everything you want. Okay, so that was the motivation behind starting this project. And another joke, how do you increase the capacity of your machine by factor 2? One thing is to go and buy factor 2 times more, which is what we usually take. We suddenly realize that we have all the ingredients there, but we are not efficiently using. So we just changed that policy, saying that only big computing facilities, big computing cores will be used to 60%. We just divided 60-40. Routine things will be done in 40. High performance computing will be done in 60. Suddenly we realized that IUCAA faculty members are running big simulations. So then JWST become important. JWST is now giving you all the challenges in forming galaxies between redshift 6 and above. So this is actually a coincidence, or we chose this project because of the success of JWST. Okay, again, this slide I prepared for normal audience where you explain what all JWST can do. I don't have to spend time here. Okay, so we'll just see what JWST has found. So this is the deepest image with JWST. You would have seen several such images taken with Hubble Deep Field. So what is big deal? But this has a much better PSF because aperture is 8 meters. And it can, since the operating frequencies are at higher wavelength, it goes much deeper. And typically, a typical galaxy peaks is around redshift 9. It is very different from what Hubble was doing. Hubble was doing around 6, 7. Now you are starting from 9, 10, 12. Second thing is that these are the highest redshift spectra taken. This is the highest redshift, 13.2 is the highest redshift of a galaxy for which we have a spectroscopic redshift confirmed. This is the spectrum of a galaxy. Of course, you will be laughing. What is this nonsense? Nothing is there. So most of the time it is like that only because low signal to noise, you don't see anything. If this spectrum is given to somebody who has never worked in extragalactic astronomy, they say it's featureless. We cannot measure anything. But all these galaxies have no flux beyond some value. Okay, so this is what is now, you would have heard what is known as Lyman breaks. Lyman breaks happen because of hydrogen absorption. And in this case, it is coming from hydrogen Lyman alpha absorption at higher redshift. So look at these galaxies. You basically see spectrum is featureless, and suddenly you see some sharp cut. And this been identified as the location of Lyman alpha. So if you take 1.5 micron divided by 1215 angstrom or whatever, 11 micron divided by 1215, then you will be able to get whatever redshift you want. So 13.2 is the redshift. There are two things which is important for us. One is that, first of all, you detect galaxies with spectroscopically at large distances. Second thing is that you have a break. Again, there is a little bit of thing. This break can be due to various things. There is a confusion, Lyman break, Lyman leakage. I think there are a lot of confusion among our community. We have to be very careful what we are talking about. When you are at very high redshift, not at redshift 1.5, 1 or 0.5, 2 or 3, there the Lyman leak is very different. When you are talking about redshift 10, what you call Lyman break comes from 1:2 bound transition of hydrogen atom. Why is this? This is because it is the intergalactic medium filled with hydrogen. If the universe is not ionized, intergalactic medium is full of hydrogen atoms, and that itself will not allow any photon with wavelength less than 1215 angstrom to come to us. So that is very different from Lyman break, which we talk at low redshift. Low redshift Lyman break is the photons which are created in the galaxy itself is not leaving the galaxy. That is because of 912 angstrom ionizing photon. So these two are not same. And when you are relating whatever measurement one does at 912 angstrom with high redshift universe reionization and all, be careful. They are all related, but one has to be very careful about what is the Lyman break, how you are measuring. And here what I am quoting is the Lyman break is the hydrogen absorption. This kind of no photon below some wavelength is not related directly to the what happens in the interstellar medium of the galaxy. Rather, it is related to the what happens outside the galaxy itself. This is the first good news, fact that you are not finding, and in fact, there is a nice thing, how the light is recovering from this part to other part, whether it is going like a sharp edge or whether it goes slowly. that gives you information about what kind of universe in which this galaxy is living. If it goes sharply like this, it is living in a region where surrounding region is highly ionized. But if it goes slowly like this, you can say that this region is highly neutral. This can be checked in the simulation. You have a galaxy. The galaxies, we know that what kind of gas in which the galaxy is living. You can actually do this. So this observation becomes interesting. Of course, just to put the perspective, this is the curve which we draw between look back time and redshift. How much time elapsed between this? For example, if I take redshift of 7, this is something like 780 million years since the Big Bang. If you take the highest redshift dial, which is around 300 million years from the Big Bang. 300 billion years means already you bringing in another uncertainty in the physics, which is related to the stars themselves. If you are talking of million years, already you are into the regime of OB stars and what you are going to do with it. 10 to the 8 years kind of, again, it's like a population you have to worry about. So the numerical effects can kick in at this level of understanding whether your stars are okay, whether your stellar evolution you can trust or not. Okay. So this is just wanted to say this is the regime in which we are going to be interested in. Okay, so in some galaxies we end up detecting these lines, not only these edges, which this is again you see below Lyman alpha there is no flux, but you can also see nebular emission like typical nebular emission one sees in galaxies. But interestingly, these nebular emission lines are not always confined to what you see in galaxy. This is one of the twists which happened from JWST. If you have just seen only this nebular emission, you will say, okay, stars are forming. I have no problem with it. People start detecting various things. I will come, so I can skip this actually. You know that same spectrum can be obtained in multiple bands. What people saw, which is interesting, is that some of these objects, some of these galaxies look very red. When you take the spectrum, it was very interesting. Suppose if you look at this part of the spectrum, they look typically like what you see in low redshift objects, but width of these lines are substantially wider. Width of these lines are of the order of 3,000 km per second or 4,000 km per second. Such large width, if you see in our universe, you would have said that these are coming from some AGN. So there must be some black hole which is following mass and emission line is producing from. So this part, if you take, it is AGN. But if you look at the spectrum is going down. AGN should go up like this. Our definition is that AGN is a blue object like star, right? That is quasi-stellar object was defined by blue. So people said that this part is beautiful. This is like a AGN which is formed in a dusty environment. So it is red AGNs which are being detected. So if you look at images, they look like this. So these goes by the name little red dots. Why are you worried? If they are like AGN, why should you bother? But if you just if you take the redshift of this guy and go to some characteristic wavelengths here, and you go beyond this, typically it is around Balmer break, around 4,000 angstrom in the rest frame. If you go beyond, if you go towards the blue, suddenly it becomes like a bluer object. So the spectrum looks like a V. If you start from lower wavelength, as you go to higher wavelength, the flux goes down. So that part of the image, if you take, it will appear like a blue object. But when you go to the higher wavelength, it becomes like a red object. So this goes by the name little red dots. Why it is important? People said that no, there is two interesting things. It's ulta of what happens in normal galaxies. Normal galaxies, galaxy light will be redder, quasar will be bluer. Quasar, if you want to detect quasar, you go to the bluer side. If you want to detect galaxies, go to the redder side. Here it is opposite. If you want to detect quasar, you go to the bluer side. If you want to detect galaxy, you go to the redder side. Is it true? Which is to be debated because this is what is our understanding. So people said that we can understand by saying that the black hole which is growing. When it becomes problematic is that JWST detect lots of these guys. The volume density of little red dots is roughly 1/30th of normal galaxies. That means every 30, one out of every 30 or 1 out of every 20 galaxy should have a black hole with a mass which is of the order of 10 to the 5 solar mass or 10 to the 6 solar mass. This is very difficult because you are talking about 300 million here, and you say that already 1/4 or 1/5 or 1/30th of these objects should have some seed black hole which is already growing. This is a very tricky problem because black hole doesn't grow like this. It starts shining in X-rays till become quasar. Now then you should see X-ray emission coming from them, optical emission coming from them. Why are they not there? So it is an interesting object, and the way the total number is calculated per unit volume, the luminosity function is a problem. Second thing is that we can also look at how they cluster. You look at in the space, are they randomly distributed or are they distributed with some structure? That tells you what kind of sources they are tracing. Two problems are there, and this is a big problem which I don't think anybody has a clean answer. So this is an open problem for us. So given this situation, okay, this is what we remember. If I look at the global star formation rate density, that means I go and put a box at different redshifts and ask how the universe is forming star. This is the plot we had before we started doing JWST. That means from redshift 8 onwards, star formation slowly builds up in our galaxy. By the time our universe reached about 10 giga-year, right? Actually, you have to do one. This is 3 giga-year because it's 10 giga-year from, I have to subtract from 13. So 3 giga-year, you will see that there is a peak activity. Later on, as the universe evolved, star formation rates fall down. This goes by the name Maddow-Dickinson curve, it's a very famous curve. But what happened with JWST? When you do the same plot, this is the expectation from there, and people are finding the star formation rate density. Instead of falling like this, it goes something like this. Okay, so these are the challenges which you have. How much time I have, depending on that, I will plan. 30 minutes. Okay. Okay. So now we are going into our simulations and then look at the results. This is very preliminary here, completely. So this is our whatever HPC, and we have about 100 compute nodes, about 320 cores. This is what the peak performance we get in our computer. We have every 6 months we are allocating about 7 million CPU for project starting from this thing, open to IUCAA associates and university researchers and IUCAA people. This is what it is now. Of course, with this success, we are able to convince National Supercomputing Mission, and they are going to give 1 petaflop machine, and this machine will be operational from December this year. So that will be roughly 3 times powerful than what I am showing now. So what are we doing at IUCAA? So this is the thing. So we this is the Nishi Kandai at faculty at NISER Bhubaneswar. He is my student Ranit Behra. So what we have done is that we are setting up high performance computing simulation, very similar to whatever you see in any hydrodynamical simulation, because code is not written by us. Code is taken from standard resources, but we have added a lot of physics, subgrid physics into this. That is the main thing. So I'll just give the list of models. We have found a fiducial model. We take standard cosmological parameter, standard efficiency of stars and all. Then we run one model with stars formed at less efficiency, one model with stars formed at more efficiency, one model where we grow black hole at high speed, one model we grow black hole at small speed. In one model, we don't have any feedback and just run. This is the idea. And typically each model will, so just to compare, all of you are familiar with TNG, right? TNG 50, 100 and 300. And just concentrate on these 3 lines. The box size will be of the order of 50, 100 and 300 megaparsec cube. One side will be of this order. This is what is TNG's box. And it was doing about 2000 particles. There are 2000 cube particle of dark matter, 2000 cube particle of baryons. Okay. So what are our boxes? So we have a box of 1000 cube particle, 2 into 1000 cube particle, 2 into 2040 particle. This is exactly very close to what one gets from there. Our box sizes we are running 3 different box sizes, 50, 150 and 200. The only difference is that they do adaptive formation. We don't do it, because of which our resolution at mass scales will be factor 2 lower. But this is already substantially bigger simulation. You can imagine. Here is a snapshot at redshift 6, and this is the small region you see, and this is the kind of already at redshift 6. You can see, if you are with a little bit of imagination, you can see a filament running like this, another filament running like this here, and we can zoom in. These are all stars, right? This is not dark matter or gas. These are all star particle distribution. So to run up to Redshift 4, our simulation take about 11 days. So each cycle, we are getting about 60 days, 40 to 60 days. So we are hoping that next year we'll have full suite of thing ready. So all 20,000 particle simulations are run at IUCAA. All 1,000 cube particle simulations are run at NISER Bhubaneswar. And just examples of some nice galaxies at Redshift 4. You can see the spirals, nice spiral, which is already there. These are the. So now coming back to what do we do? In fact, what we do is that we pixelize the typical galaxy we detect. We pixelize them, and each pixel means like it is. You imagine pixelize them means what? This is the 3D box, and if I take this is the pixel of my observation, this goes through like a tube which goes in. So we count all the stars which are there. The stars will come with different ages. Stars will come with different IMFs and whatnot. We take care of that and synthesize the spectrum. So here, example is given here. If you can take at edge or you can take at the center, spectrum will be very different. So you can actually do spectral in our simulation. So each pixel in our simulation can give you spectrum. The spectrum can also take care of simple starlight. It can also have nebular emission. So we have incorporated cloudy kind of radiative transport into the system so that this can be there. So you can also have a filter and take an image of any of these JWST filters, you can get these images. And I will also give you some examples of what happens between two feedbacks, just for the sake. So we have two simulations. Everything else is same in one simulation. We make star probability for forming stars slightly higher than another simulation. So this is what we call weak wind simulation. Weak wind simulation is the simulation in which the galactic winds are not very efficient, so they are not pushing a lot of gas outside. So in these cases, you find that more stars are formed. And the same simulation, everything else is same. You can see the difference. For example, this is one of the image of the same galaxy when the feedback is changed. In one case, we have fast wind going. Another case, there is no fast wind. Actually, this you can. I don't know whether you visually see any difference, but you can clearly see this galaxy has about 42,000 stars. This galaxy has about 26,000 stars because the dark matter, everything else is same. So this gives you an understanding that if I just change the speed at which the winds are propagating by 30%, we are gaining twice the number of stars in the same galaxy. So this is the kind of, I think the interpretation can be interesting, but you can now look at the spectrum. Our fiducial model has a spectrum like this. Weak wind model has a spectrum which is going like this. All other things are same. Amount of gas in the halo is same. Dark matter thing is same. Only thing we tube is to say like this: when stars are formed, we will send smaller winds compared to this. So you can clearly see a galaxy will look bluer or redder depending upon the feedback. In fact, the galaxy will look bigger or smaller depending upon the feedback. If the feedback is weak, most of the stars will be formed in a smaller region. Large number of stars occupying smaller volume means they will be brighter. So easy to detect them. This is what makes them easy to detect. That means they will boost the number. Having said that, now we'll look at the luminosity functions. What do we achieve with our simulations? These are very preliminary results. Nothing is published because it's all going on because last 6 months only we are doing. So these points are basically red points are from Hubble Space Telescope, blue points are from JWST. You take any one of the curve come from one of our boxes. So if you take blue, this is coming from 250 megaparsec cube box. So what happens in this thing, when we fix number of particles and box size, what we call as the mass resolution is fixed. So if I keep the number of particles same and make boxes smaller and smaller, I will be able to detect smaller and smaller masses because mass per unit volume is changing, density is higher. So that's what happened here. If I take a bigger box, I will not be sensitive to detecting fainter galaxies because they are not there. This is a numerical artifact. So any curve, when it turns like this below, this region you cannot trust because that is incompleteness in your simulation. This is why what we do is that we don't run one box, we consider different boxes. Okay, so now you can see when you run the blue curve in the overlapping scale where this curvature is not there, you see two curves are matching. Red curve is the same simulation with all similar conditions, but the box is 100 megaparsec. So when you go here, same thing, this guy turns around here, but if I do 50 megaparsec, and you see this, We have not done any matching, it just sits on top, it just tells you if such things happen, in technical term, it is known as convergence is perfect. Means like I am running 3 different simulations and I'm just seeing that in a overlapping scales, the results are matching. This means that, okay, your physics may be doubtful, but your code is not wrong. So this, okay, so at least the regime in which we are dealing with, we can trust the numerical result, but you can question the physics which you have put in writing this thing. The first part I want to say is that just concentrate on this part you ignore. If you ignore that, you will see that there is a nice follow-up of luminosity function at redshift 7 without any problem. But there is a problem which you see at the brighter end. Brighter end, observations are here. We are overproducing the galaxies. Overproduction is never a problem. If you produce less, there is a problem. If you produce more, you can do it. And one of the technique which we will use is to say that these are massive galaxies. They build up a lot of metals. When they build up a lot of metal, they would have come with a lot of dust. And if you actually, this is in UV, you need to put little amount of dust only, it will redden the galaxy. And we also figured out AV of 0.3 to 0.5. If you introduce in your galaxy spectrum, you will be able to match this part. So this is not an issue. So we have not yet done because I don't want to do it by hand. I want to actually put a physics which will connect star formation, metal production to dust depletion. So there are some standard things which we are implementing. Once this is done, this part will be also taken care of. Now let's just look at what happens to these 2 models. So this is my observation, same observed points. Black is what I shown. This dotted thing is when I include light coming from the diffuse emission. So this one is my weak wind. Weak wind model means like I make star formation more efficient. And you can clearly see the luminosity function is shifted brighter, which means that at redshift 7, whatever model I thought as my fiducial model is reasonably good. I don't have to reduce the star formation efficiency. If I reduce, I find it moving like this. Of course, you want to bring it back, then whole region, I have to depend on what I do with dust. It's not a good idea. Okay, so we can clearly see at redshift 7, there is one more curve I put here, because this is what we have been worried about. This curve, I asked my student to play like the way it has been done in low redshift. You take one point and say that I will use constant mass to light ratio just to see what you get. And I think this gives a better fit compared to our simulations, right? This is basically dark matter potential in our box. We just assign one light, that's it, the ratio. And it goes through all this. So you will see like, okay, a simple light to mass conversion seems to be working in this region. Of course, when we have a curve, we should not worry about one point. We have to look at all other points before drawing the conclusion. So this is at redshift 9. Again, forget about these parts. And I'm sure I don't have to tell you that these models are okay. Up to redshift 9, we don't have any problem. This is nothing is being tubed, just taken directly from the observations. Of course, let us now think what our model predicts in this way. So these curves are plotted at different redshifts, 7, 9, 11, and 13. So clearly the numbers should go down. The way, because we are not having dark matter potential, the numbers should go down. And if I take any luminosity, I should find the numbers increasing as I come towards the lower redshift. So this is the prediction from the model. So what do you find? So I'm just giving you this. This is redshift 7, same plot. So this is the curve which we got from for our one of the box. Now you see they are not fitting because I'm showing only one box. If I show all the box, you will see that if I chop this part and use appropriate thing, you will see it is going through all of them. And this is what is expected for redshift 7. This is what is expected from our model for redshift 14. And JWST is saying galaxies are here. So this is what you find in newspapers, saying that there are more JWST galaxies than what has been predicted by this. And you will say that why did you build all these things? This kills your model. By the way, the interesting thing is that I went being an observer, I also went back and looked at the data. None of them were spectroscopic redshift. Each bin, the number of galaxies detected is 1 or 2. Root n itself, one galaxy root n means, in fact, nowadays people come up with various statistics to say like if the number is 1, 2, 3, The Poisson error is not root n. That is just to avoid being 0. But as far as we are concerned, the whole thing, that's what I said. The number of galaxies are very small in each bit. Should we panic now itself or do something about it? So we are trying to do something about it, but I am not panicked. Because this same situation happened when Hubble Deep Field happened. There are publication of huge amount of massive galaxies at redshift 8 and 9. People said that Lambda CDM is in great trouble by Mobashir and company. For several years, people were worried about various matter models and all. Then people figured out afterwards, these were all at redshift 3 galaxies fitted with wrong spectral energy distribution. Till we get large number of high redshift spectroscopy will confirm galaxies, we have to fine tune. So I'm not going to give up. So at least two news for us. Below redshift 10, it seems you are more or less on the ballpark. So why can't you focus on that region? Higher redshift, we will wait, but these models will be already ready. We will make predictions and it out. So this is my last slide. So what you can do with it? So galaxy evolution, this is a kind of publicity. Anybody wants to look at some data, you are most welcome, because we don't have that many hands to do it, because we are doing basic level modeling, but we can make it available data to you. Galaxy evolution, including size evolution, we are able to measure sizes very precisely, and size will depend upon feedback and other processes. If somebody is interested in studying this, it's okay. I come back to my own problem, metal enrichment. How are you enriching the intergalactic medium and interstellar medium by metals? Standard relationship. We know that black hole versus galaxy, galaxy main sequence, mass metallicity relation. These are all known at low redshift. We can ask this in the simulation where this relationship was set up, at which epoch these fundamental relationships are formed, and how you can change the epoch by playing with the feedback. You already see this black hole mass versus this relationship. I didn't talk about black hole. We actually form black hole. We also take spectrum of the black hole self consistently and look at the feedback processes. And we are clearly seeing that relation, Gregorian relation, is not there at high redshift. It builds up around redshift 5. It's a very interesting problem to do. IGM and CGM evolution, so we can have each galaxy. Now we look at how gas surrounding these galaxies are populated with metals. So we can do, for example, Muse spectrum. We can produce Muse band spectrum from our simulation box. I'm trying to convince some of my people to see like whether they can get involved. Ravi, you should also consider doing that. Then, of course, cosmic reionization. One can build models of reionization. Again, another student is working on looking at that alignment of absorption. I told you whether it goes straight or whether it goes like this. There we are able to distinguish the absorption coming from interstellar medium, circumgalactic medium, and infalling intergalactic medium into this, and there is kind of scope for people to. Of course, we are giving merger histories of galaxies. Each galaxy, we are storing at a very finer interval in our simulation. We can simply say how you built one galaxy, starting from all these things, and which galaxy is affected by AGN, and all this tracking we can do. Of course, one of the things I have to say, we are also able to quantify what is the GW background, because there's merging black holes, supermassive black holes. We can actually get the volume densities of these very accurately under different scenarios, and we can forecast what kind of detections you will have in these experiments. That's all I want to say.
Thank you, Professor Anand, for a very clear and nice talk. So before we go over to the Q&A, I would also request our director to present you with a token of our appreciation. Thank you, Annapurni, and I think we can go over to the question and answer session, so is that fine? So, yeah, questions. Anusha.
I don't work in Galaxies, but I have one night question. So, there's a lot of things put into these simulations. So, is there any problem with the uniqueness? Like, can different combinations of certain things give you the same result?
Yeah. So I think that's why I qualified the statement I made. I just wanted to check whatever I see as an observer and interpret, how does it lead to this? Clearly, there is no uniqueness to this. For example, when I said probability of star combination I reduced by something, I could have done by changing some parameters. This is what we have done in the simulation. But while presenting the talk, I never said that this is due to velocity being slow or mass loading factor being large. I think the interpretation we are not saying. We are just seeing that if you form stars less efficiently. Now your question is that how are you can form stars less efficiently? They will be degenerate. So that is where cleverness of finding unique thing will be interesting. So I will not go into any parameter and say this parameter drives this. I think that will lead to mistakes. I agree.
Rakesh.
So I was just wondering that what are the physics which are put to pull the baryonic matter when they are falling in the dark?
Yeah. I think we in these simulations there are two things which are happening: heating and cooling. Heating is through two processes, three processes actually. One is that basically shock introduced by the collapsing matter, because this is what you call Fourier shock. Then we have background radiation which constantly heats something, so gas cannot cool. There is a floor below which the gas cannot cool. Third thing is that any supernova ejection will heat it. Cooling is basically depending upon the temperature. So if the temperature is very high, we will do free cooling. If the temperature is lower, we use the cooling curve. Cooling curves basically there are various options given. We use a cooling curve which is includes metals also, but at the average metallicity of the galaxy. See, each particle you can do cooling, but there are also options that do an average cooling kind of. So that's what we do. So we do use cooling curves, but these cooling curves with radiation field.
This is enough to compensate the expansion time scale which we have, because if the cooling is not fast enough, we will not form the clustering, right? Gravitational collapse.
So I am talking at scale where we don't care about it's after the galaxy is turned around. So there is no expansion here. So you know that, not turn around. So only those regions where it is turned around, we call it as halos. If it is still expanding, it will be IG.
The question I had is a very simple one. The mass to volume ratio is equal to as a constant. So that's must take the law. So what kind of a functional form fits?
Functional form for mass to light.
Yes.
Yeah. That see, this is what we have done with Kandu. If you are at a higher mass, you do that m to the power 1 by 1 plus m by m12 to power log at a -3. Yeah, -3 is a power law cut beyond a mass scale. So that will explain AGN feedback. AGN feedback is suppressed by a power law cut. And the lower end, usually that is not very clear. This is the kind of model, for example, Keith and all. So I also we work together. These models we do like this. We have a suppression, which is a parameterized suppression. So that will ensure deviation from constant light.
Very interesting talk, Siva. So I have a question regarding the JWST results. So assuming that, let's say, you expect a small number statistics, assuming that it is correct, do we have any direction for explaining these transformations which happen?
Yeah, the fact that up to redshift 3, redshift 10, most of the models are consistent with Lambda CDM. It will be very difficult for us to argue that I will change it at this stage. But there are some freedom in your hand. One freedom is that while converting star formation rate and stars into light, I have to assume some IMF in this thing. For example, if I go to top heavy IMF, I can gain a factor 3 in the light, so 1 or 2 magnitudes, but we are still debating. See, if the numbers are not this high, but reduced by factor 2, you are within ballpark to explain. So this is what we are trying to do. What from our side, what we can do is that in these simulations, we consider all possibilities and give what best one can produce with CDM. That is the idea. Afterwards, by that time, if the observations are still not there, one has to worry about it. People are now talking about something beyond Lambda CDM because actually the problem is not very massive halos, because that is a mistake. Theoreticians think that is galaxy which you are detecting are very massive. So they think of how to make massive halos collapse quickly. What we have to do is that we have to find some way of forming stars very quickly.
Yeah.
This dark matter wise, they are intermediate mass bending. This is what I realized last week. We're still thinking how to do it, but we will produce standard things. For example, if you stop away IMF or use an IMF with low mass cutoff, not at 0.1 solar mass, but around 1 solar mass or something, arguing that these are all metal poor galaxies, you cannot form small stars. All of them will boost light, but they will not boost by factor 10. If one becomes correct, we have to think of something else.
That like incident.
Yeah. Another possibility is that most of these guys is fainter end. They are detected through what is known as the legacy field, where they are lensed by a foreground galaxy. That's why they reach smaller depth. We may have to worry about the lensing models. I will not go into that now, but our thing is to just to predict how much you can push our model, which does well below redshift 10, right? If redshift 10 it fails, I can leave this model. Fact that it is fitting well. Now we have to see like what we can predict, and we can also calculate, for example, what should be the volume you have to observe so that you can confirm our result. So this is one pointing, you get something, you may be lucky. So this is again goes by the chance questions, which we can test in our simulation. Take the same beam, like JWST image, put it and find out what is the probability that you will get this. That we can do.
I have one more question on your computing facilities. So the petaflop NSM facility, is it only for IUCAA or it's going to be a national?
National.
You have to pay for it first.
Yes.
In a sense,
You pay for it to get the
I don't know. I didn't know about pay for it. So you always pay something, right? So we are setting up all the data center facility, power supply. So it will be on our head, but maintenance will be by them. I don't know what it is. And definitely it will be free for universities because that is our mandate. It will go into our budget. But when you are making 60% free, 30% can be easily. I am hoping that it will be. That is the thing we said. It will be available to through tap or something. I will tell you December once we set up how it is running. It's 40% GPU, 60% CPU.
Motion added. Yeah, thank you for the talk. I was wondering, you spoke a lot about galaxies, but what about the large scale structure? Have you compared it with not just observations, but also with other simulations? Are you getting similar kind of structures?
Yeah. I think these simulations, for example, Astrid, we are getting power spectrum exactly like Astrid. That is one of the, instead of clustering, you can look at the matter power spectrum. We are getting that one. But clustering, somebody has to do. It's available. So, but we can show that matter power spectrum and several things we have reproduced more or less what people are finding in Astrid. So one of our fiducial simulation is exact parameter of Astrid. We are getting all the parameters exactly.
What about comparison with other simulations like PNGP at any particular redshift, for example? Are you getting similar structures?
We are spending all the time generating images and spectra. This will be done at some stage. We have not at time. Okay. But quick way of comparing is the power spectrum, right? Matter power spectrum will give you the clustering that we have looked at.
Ask Dr. Mike.
It's also on Zoom. So.
Zoom.
Okay. Hello, is there any physical motivation for considering that mass to light ratio will be constant with all over the mass scale?
No, no.
Because the reason I'm asking, because from the stellar to halo mass stellar relationship, we see that there is a bend. And on the higher stellar mass, there is not halo mass included. And also the relation changes over the ratio.
These are wish list. Constant mass light ratio is wish list. And such a thing is easy because it is easy for you to predict luminosity mass function of halos because there are analytical prescription. If some simple scaling relation works, one will be able to do a lot more. So these simulations will be very less expensive. If you find some analytical way of connecting light to dark matter, it is not physics-wise correct, but it is very useful for doing statistics. At least you can see what kind of universe you need, what kind of data you need if you want to constrain some parameters. There is a lot of effort going on to take pure dark matter only models to map various properties of galaxies so that large scale structure and all, people believe that it can be done at 1% level. That's why a lot of effort is there. So it is not completely hand-waving to look for associate only pure dark matter simulation and associating some light with it. That is okay. That people do. But they do with something called halo occupation distribution and complicated things like this. I went for a simple thing for a talk, but nobody does this constant mass to light. In a paper, nobody will write.
As a function of the. If this halo mass is a function of the mass, then also these curves can be fitted, I mean, with observation.
That's what I'm saying. This is what is yeah, fine. This is what she also asked. Any deviation from one value. We know I myself have done that at some stage. We have a power, if you put a power law cut, higher end can be fitted very nicely. There is no need for it. Lower end, we have to play a little bit with the mass dependent efficiency you have to put, but it can be done. It is done. This paper, what I'm talking is in 2007-8, not even recent. So these are well-known things.
So I have some simple questions on the simulation. So this 1024 or 2048 cube particles that you're talking about, so each particle is representing some mass. So is it only baryonic mass or dark?
No, that's why 2 into means like 2 times this thing.
One is
dark matter, one is baryon. And once the run starts, you will also create one more, 2 kinds of particle we create. One more particle is star particle. That number maximum will be decided by how many maximum gas particle I have.
particles in one.
And we also have black holes. At some stage, we see the black holes in the gas. So black hole is another set of particles.
Black hole is seed.
Seed.
You cannot like counting the number of particles.
That cannot be
Not
done
by
because our
density.
particle is like a star cluster. Our best resolution is 10 to the 6 particles is one part. 10 to the 6 stars is in one particle.
I see.
So we will not do the counting that way.
And what about the gas? I mean, it is just N. There's no thermal. There's no Navier-Stokes equation or anything like that. Apart from this.
I don't know Navier-Stokes equation or whatever, but what we know is that for each star particle, so many properties are associated. We can also have what fraction of the star particle is in the cold neutral medium, warm neutral medium, and hot gas. And we also have metallicities. We also have the probability that this star particle will eventually become a star at some stage. And we have temperatures.
So there is thermodynamics.
Full hydrodynamics.
Yeah, okay. If other questions on the Zoom, for example, Vikrant? No, okay. Okay, if there are no more questions, then let us thank the speaker again. Let us proceed to the East Lawn for the group photo, and thereafter we go to the West Lawn for the tea. And an important announcement for tomorrow, because from tomorrow onwards we have packed program for the last 2 days of the in-house. Please if you are using your own laptop, please make sure that it works, the presentations work. And if you are uploading on the auditorium laptop, please do so beforehand. Right? Okay, let us now proceed to for the group.